Have you ever stopped to consider the remarkable discoveries in experimental physics and astronomical observations that have transformed our understanding of space and time? From unraveling the fabric of the universe to exploring the intricate relationship between time and reality, these breakthroughs have reshaped our perception of the cosmos. So, have you ever wondered how space and time intertwine and influence the fundamental nature of our existence? Join us on a captivating journey as we delve into the depths of space-time and ponder the profound question: how do the dimensions of space and the passage of time shape the very essence of our being? Welcome to Revel Discovery, your portal to a world of fascinating discoveries and awe-inspiring insights that will expand your understanding of the universe and beyond. Hey there! We're absolutely thrilled because we've managed to capture some truly rare experimental evidence that delves deep into the fundamental structure of space and time. It's a fascinating subject, and we can't wait to share it with you. You see, space and time are not just random concepts floating around independently. They're intricately intertwined, especially in the context of Einstein's theory of general relativity. According to this theory, space and time are inextricably linked in a four-dimensional space-time continuum. It's like they're dance partners, moving together and influencing each other's every step. But here's the twist. This is not as straightforward as we might think. While it is commonly seen as a measure of the progression of events, some alternative theories propose that time is not an inherent property of the universe, but rather a human construct. It's a mind-boggling idea that challenges our conventional understanding of time and opens up a world of philosophical pondering. Now let's dive into the fascinating connection between gravitational masses and particle pathways in Einstein's space-time theories. In Newtonian physics, the masses of objects determine the total gravitational force at any given location, which in turn determines the acceleration of particles based on Newton's third law. It's a relatively straightforward cause and effect relationship. But in the realm of general relativity, things get more complex and mind-bending. To predict the path of a vector particle, we need to solve Einstein's equations for a specific scenario, which helps us identify the unique structure of space-time associated with that situation. But that's not all. We then need to tackle a second set of equations to predict the trajectory of the particle accurately. However, even Einstein, the genius himself, faced challenges. While he could derive some effects, like the deflection of light when it passes through massive objects such as stars, by invoking the general principle of equivalence between the effects of gravity and uniform acceleration, there were still aspects that eluded him. The precise nature of space-time and its behavior in intricate scenarios remained an enigma. That's where general relativity steps in. It's Einstein's groundbreaking theory that defines the very fabric of space-time and provides us with predictions about the awe-inspiring phenomenon of the Big Bang. But hold on, it's not as simple as just plugging in some numbers and getting a definitive answer. There are various mathematical approaches, and cosmologists have been engaged in a tireless quest to discover the most accurate one. Here's the mind-blowing part. All these mathematical solutions share a common feature. They contain a singularity. A singularity is a point in space-time where certain concepts become infinite, while others unhelpfully become zero. It's a mind-bending concept that challenges our understanding of the laws of physics and demands further exploration. When we physically evaluate this scenario, we find a high density of matter in the universe at that moment, which is why it's called the Big Bang. But the singularity raises many questions. What happened before the Big Bang? How did the process start? General relativity, as remarkable as it is, hasn't been able to answer these questions definitively. The prevailing consensus is that the origins of the universe lie in some massive quantum events. But this assumption might still hold true if we explore it through a more comprehensive theory of quantum gravity. In recent years, numerous mathematical cosmologists have seriously considered the hypothesis of a pre-Big Bang era, adding more layers to this mind-expanding journey. And that's where cutting-edge technology like the James Webb Space Telescope comes into play. It's an incredible astronomical instrument that pushes the boundaries of our knowledge about the cosmos. By observing distant objects and events, the telescope allows scientists to collect crucial information about the early universe exoplanets, star formation, and various cosmic processes. Just recently, the James Webb Space Telescope astounded us with a remarkable discovery. As it orbited a staggering 1 million miles from Earth, it captured the captivating image of a galaxy cluster known as SDSS J1226 plus 2149, located approximately 6.3 billion light-years away. This cluster is so densely packed with stars and planets that it distorts space itself, creating a mesmerizing visual effect resembling a bowling ball sinking into a mattress. The researchers behind this discovery are hopeful that by studying the celestial objects and their interactions within this cluster, we can gain profound insights into how space and time interact on cosmic scales. And there's something even more mind-blowing. There's a massive cosmic lens between us and the objects behind SDSS J1226 plus 2149. It's like a giant magnifying glass that allows us to peer into the depths of the universe. Gravitational lensing, as this phenomenon is called, occurs when a massive celestial object such as a galaxy cluster causes space-time to curve significantly, bending light around it. The James Webb Space Telescope's image reveals astonishing instances of distorted light resulting from this warped space-time. One particular marvel is the appearance of the cosmic Sirius galaxy, a stretched-out red arc near the lens, vibrant, bright, and considerably thicker than its surroundings. This awe-inspiring image was captured by Webb's main near-infrared sensor, part of a mission focused on exploring the early stages of star formation in distant galaxies. Webb's mirror, spanning over 21 feet wide, is an engineering marvel that collects an astonishing amount of light, surpassing even the renowned Hubble Space Telescope in size. The James Webb Space Telescope mainly operates in the infrared spectrum, which allows us to observe a significantly broader portion of the cosmos. Infrared light, with its longer wavelengths, can pass through cosmic clouds more effectively, avoiding dispersion by densely packed particles. This unique capability opens up a whole new realm of exploration, unveiling celestial wonders that were previously hidden from us. Gravitational lensing, in addition to its scientific significance, has an unintended consequence. It magnifies distant celestial objects. This fortuitous effect has been instrumental in unveiling some of the most distant galaxies ever discovered by humanity. One striking example is the extended, brilliant, and distorted arc that spreads out towards the center of the image, the cosmic seahorse. Its brightness has been significantly amplified by the gravitational lens, allowing astronomers to observe star formation within this remote region of space. With the James Webb Space Telescope's extraordinary vision and state-of-the-art sensors, scientists anticipate shedding fresh light on the intricacies of star formation in faraway gravitationally lensed galaxies. Based on our current understanding of galactic evolution, the earliest generation of stars in the universe consisted mainly of hydrogen and helium. Over time, through nuclear fusion, these stars gradually produce heavier elements such as carbon, nitrogen, oxygen, silica, iron, and more. When these stars eventually exploded as supernovae, they spread these enriched elements into the interstellar medium, paving the way for the formation of subsequent generations of stars. Time, my friend, is one of the few constants in our lives. From the dawn of the cosmos to the present moment, it remains the interval between the past, present, and future. Civilizations rise and fall, stars are born and die, and our system of recording and comprehending these events in relation to the present remains steadfast. However, through the lens of the James Webb Space Telescope, we're starting to grasp the complexity and sheer wonder of time. Have you ever found yourself contemplating the mysterious interplay of space and time and how it shapes our understanding of the universe? What if I told you the recent groundbreaking discoveries have challenged our conventional notions and opened up new possibilities? Engage with us by leaving a comment, subscribing to our channel, and clicking the notification bell for regular updates. Keep watching, stay inspired, and get ready for more exciting discoveries. See you in our next episode.